Hello, my name is Chloe Luyette. I'm a senior chemical engineering student at Wayne State University, and today I'm going to talk to you about my research regarding the effects of fluorination on the interfacial properties of alcohols. Now, if you are familiar with surfactants, you know that they are chemicals found in a myriad of industrial products that we, as consumers, utilize on an everyday basis. Some products that you might be familiar with include soap, water-resistant clothing, and coatings on pans and other kitchenware. They're used for applications that require the favorable interfacial properties characteristic of surfactants. Nonetheless, increased usage of these products can be harmful to the environment. In particular, fluorinated surfactants have been found by other studies to not only accumulate in the environment, but to also have harmful, even toxic side effects to both humans and wildlife. Studies have shown that prolonged exposure to fluorinated surfactants can cause various types of cancer and birth defects. Because these compounds are so toxic, they're very difficult and dangerous to work with in an experimental laboratory. This is where computational research comes into play. In Dr. Potoff's lab in the Chemical Engineering and Material Science Department, we try to decide which computational tools are the best for predicting desired compound behavior, and then we aim to prove the general reliability and to describe the accuracy of our predictions. Conventionally, 1-octanol water partition coefficients are used to determine the bioavailability of a compound. By predicting the 1-octanol water partition coefficient of fluorinated surfactants, we could potentially inform the development of a compound to use instead of surfactants in industry, or inform the development of a method to promote the degradation of the surfactants before they accumulate in the environment. 1-octanol water partition coefficients are calculated via the equation here above Table 1. Here, the change in free energy of hydration requires solvation of the solute of interest in water. These results were published by a previous undergraduate student who worked in my lab and are referenced in the bottom right corner of my poster. On the other hand, the change in free energy of solvation requires the solvation of the same solute of interest in another solvent, that being 1-octanol. To perform these solvations in 1-octanol computationally, we are using a united atom force field called TRAP and an SPC water model to create our system, and then running a free energy perturbation, or FEP, calculation. FEP calculations require NVT molecular dynamics simulations, in contrast to NPT simulations, which are run at constant moles, constant pressure, and constant temperature. NVT is constant moles, constant volume, and constant temperature. For each FEP calculation, 2 simulations must be run, a forward and a reverse transformation, the only difference being a single parameter in the configuration file called lambda. The forward transformation causes the solute to go from non-interacting at the beginning of the simulation to fully interacting by the end of the simulation. In other words, the molecule appears in the solvent of 1-octanol. The reverse transformation causes the opposite. The solute goes from fully interacting to non-interacting. In other words, the molecule disappears. By repeatedly performing the forward and reverse transformations at each of 50 windows along the z-axis of our 30 by 30 by 30 angstrom cubed box, we get decent convergence of the results demonstrated by this parse FEP graph in Figure 2. Now, Table 1 reports the results of 1-octanol water partition coefficients for fluoroalcohols up to 8 carbons in length and fluorotellumer alcohols up to 10 carbons in length. From Figure 3, we can see that compared to 2 experimental reports, our results seem to be in agreement. However, as the number of carbons increases, results seem to deviate. To predict why there might be fluctuations and change in free energies of solvation, we analyzed some radial distribution functions of our same systems for 2 interactions. The first between the oxygen of the solvent and the oxygen of the solute, and the second between the oxygen of the solvent and the alpha carbon of the solute, the alpha carbon being the carbon closest to the main functional hydroxyl group. From analyzing these radial distribution functions and observing the same interactions themselves in Figure 6, we determined ultimately that the 1-octanol microstructure around the hydroxyl group and alpha carbons demonstrated that fluorination of the alpha carbon has less of an effect on solvation in 1-octanol than in water. To sum up, trap force field was found to provide reliable predictions for the solvation free energies and 1-octanol water partition coefficients for perfluorinated and fluorotelmer alcohols, predicting some experimental data to within 7%. We believe that this method is accurate enough to provide some insight into physical properties of compounds that otherwise could not be determined experimentally for safety reasons. Well, thank you for listening to my presentation. I would offer to take any questions, but that'll have to wait until the official Student Innovation and Design Day. Thank you.